Hi, in this video I'm going to start the topic industrial chemistry. So let's get started. First of all, we will briefly talk about some importance of industrial process. Now, industrial process make industrial products, and these products are able to improve our living standard. However, these industrial process or the production of these products will have advantages and disadvantages to our society, to our economics, and also to our environment. And we are going to explore these aspects, but instead of giving you a very overall general ideas, I will actually illustrate these ideas using two examples. We have petrochemistry as well as production of vitamin C. So let's have a look. For petrochemistry, basically petrochemistry involving using petroleum, using natural gases to make a range of different products. These products could be fuels. These products could also be addition polymers such as plastics. Some were also responsible for making medicines. Okay. Now, advantages of petrochemistry, of course, they will attract overseas investment, right? Because it's a huge market, huge industry. Every places require plastics, require medicine, require fuels, isn't it? So that would be attracting overseas investment, providing job opportunities, meeting the needs of local people, right? These are something beneficial to the society, beneficial to economics. However, we know that the exploitation of petroleum and natural gases will damage the natural habitats, especially the ocean, the seabed, knowing that the crude oil, the natural gases, they are buried deep under the seabed. So drilling down to the seabed will definitely destroy the landscape, destroy the habitats. Also, this industry will produce a lot of toxic waste that will definitely endangering the environment, endangering the habitats, the surrounding. Water or solvents. Water is a little bit better, but solvents, especially some organic solvents, they may be carcinogenic, they may be toxic, and simply the release of this solvent may lead to water pollution if they are not treated properly. Down here, we have a term that we often hear, not in chemistry but other subjects, we call sustainable development. Now, I understand that for different subjects, they will have different definition for sustainable development. In chemistry, we take it simple. We say that sustainable development is understood by the development meeting the needs of the present, without compromising the ability of future generation to meet their needs. Basically, we want to satisfy our needs, but we want to make sure that our future generation can also satisfy their needs. Now, why do we have to talk about this? Because we are emphasizing sustainable development, and definitely petrochemistry or many industrial process is playing an important role. Safeguarding the environment is one of the key to achieve sustainability. Okay, so this is something you have to at least briefly know about it. Now down here, the production of vitamin C may give you a more authentic idea. Okay, now for production of vitamin C, before we produce vitamin C from sorbitol, and then basically we go through a series of steps involving fermentation and also involving some chemical synthesis, chemical reactions. And those chemical synthesis often associated with hazardous chemicals, or often associated with toxic solvents or harmful solvents. So these later steps may create a lot of pollutants, may create a lot of pollutions, and this will definitely compromising our environment. Now, the new industrial process that is implemented is called the two-step fermentation process. And this two-step fermentation process requires two stages of fermentation instead of one. So this second fermentation is used to replace some of the chemical synthesis. In this way, it can reduce the use of toxic chemicals, toxic reagent, also minimizing the use of harmful solvents. So this way, it can improve the process by producing less waste and therefore safeguarding the environment. Okay, so this is considered as an advancement of industrial process which is conducive to sustainable development. Okay, so here you see both processes begin with fermentation. In Reinstein process, it is followed by a series of chemical process. No good. But in a two-step fermentation, it replaced part of the chemical process with a second fermentation. All right. So these are the parts you may have to consider. Okay. So that would be some examples or some discussion related to the importance of industrial process. Now, next page, we start to talk about something important. In the early part of industrial chemistry, we will focus a lot in the rate of reaction. Knowing that rate is a very important consideration when it comes to industry. Everyone wants to have their process operating as fast as possible so you get the product as soon as possible, right? So that's why the consideration of reaction rates is very important in industrial chemistry. So that's why we have to have a look. Now, let's just say we have a reaction like this. Cyclopropane becomes propene. We monitor the concentration of the only reactant over time. Obviously, the reactant concentration decreases as the reaction proceeds. Now, here, we register a bunch of concentrations at different times. So then we will plot a concentration time graph. We learned this in our core syllabus. Now, you see the curve. It is a curve because you know that the reaction is faster at the beginning since the concentration of reactant is higher, so the collision frequency is higher. Okay, and towards the end, the reaction becomes slower. Okay, now, so after we plot the curve, we want to find out the instantaneous rate at 3 different time points. We want to find out the instantaneous rate at time equals to 0 minute, time equals to 10 minutes, time equals to 25 minutes. Okay? And to find out these instantaneous rates, basically we construct a tangent to the curve at different time points. And then we find out the slope. And the slope would be the rate. And this is what we have. We find out all the rate, and we also tabulate it together with the corresponding concentration of the reactant. So we have some reactant and the corresponding instantaneous rate. Okay? Now, using these data, we will plot a rate concentration graph. Now, this graph is something new to you. Okay? Rate concentration graph. We want to find out the rate of reaction, and we also want to see how it is related to the concentration of the reactant. So, these 3 points is basically talking about the rate at 3 different concentrations. Now you notice that these 3 points forms a straight line passing through origin, isn't it? Straight line passing through origin. That means the rate of reaction is directly proportional to the concentration of cyclopropane. So here, rate is directly proportional to the reactant concentration. Okay? So if you put it into an equation, then we can write down rate equals to K times concentration of cyclopropane. And K is a constant. K is a constant. Okay? Now, this is what we call rate equation. Rate equation. And later on, we will deal with a lot of concepts and problems related to this rate equation. Okay? Now, also notice that rate is a constant, and this is called rate constant. Rate constant. And this expression is known as the rate equation. Okay? Alright. Now, before we move on, think about it. If the K is a large number, then just make up some numbers. If K is like 100, 100 is a big number, right? Then you only require a very low concentration to achieve a reasonably fast rate. Do you agree? Do you agree? Because k is large, right? On the other hand, if k is a very small number, like 0.001, then you notice that even you use a large concentration of reactant, you can only achieve a reasonably slow rate. Okay? So you notice that when k is large, that means, okay, the reaction is fast. Okay? The reaction takes place pretty fast by itself. So you don't need a very high concentration to achieve a reasonably fast rate. Okay? So if I give you an example, let's just say we have neutralization between acid and alkaline. So for this reaction, if you form the rate equation of a neutralization reaction, I can say the K must be very, very large. Because neutralization, we all know that, it takes place almost instantaneously. Once the acid and alkaline mix together, the reaction is done, the reaction is complete. Okay? So those reactions should have a very large K in their rate equation. Okay? So now you have a first brief idea about rate equation. Now let's have a look at the other part. Now the other part here is something new, something perhaps a little bit abstract. We call it order of reaction. Order of reaction. So in Chinese, order means order of reaction. So now let's have a look at this general hypothetical rate equation. Now you see rate equals to k times a to the power x, b to the power y, c to the power z. Now you notice this form is similar to what we have just now. Okay? Rate equals to a constant multiplied concentration, multiplied by the concentration. But here we have A, B, C, 3 chemical species, and we have to look into their concentration together. Now that makes sense because if the reaction involving 3 chemical species, then the concentration of each chemical species should be considered because all of them might affect the reaction. Okay? So that's why the rate equation must consider all the reactants. Okay? And then we see how much they affect the reaction. Okay? Now, as to how much they affect the rate of reaction, you can also tell not all the reactant affects the reaction equally. Some reactants may speed up the reaction to a greater extent than the other reagents. Okay? So how can we describe the extent of effect of a reactant on the reaction rate? How can we quantitatively show to the people what extent a reagent can affect the reaction rate? So this is why we need this rate equation. This equation allows us to understand for each reactant what are their extent of affecting the reaction rate. Okay? Does it double the reaction rate? Does it quadruple the reaction rate? Or does it have no effect at all? Okay? So let's have a look at the details. Now, K, like I said, rate constant. A, B, C, concentration of reactant A, B, C respectively. X, Y, Z is what we call the order with respect to A, B, C respectively. This order basically tells you to what extent this reagent would affect the rate of reaction. Okay? The higher the order it is, the more effective is it to affect the reaction rate. Okay? So you see, X is the order of reaction with respect to A, Y is the order of reaction with respect to B. Now look at this is how we usually use to describe the order, okay, with respect to what with respect to what. Okay? And we say that the overall order of reaction is X plus Y plus Z. That is also making sense because you notice that each reactant has its own order. Then if you look at the reaction as a whole, then the total order, the overall order would be all these X, Y, Z added together. Okay? And this overall order reaction will give you an idea that how many reactants are playing a part in affecting the rate and the extent of them affecting the rate. Okay? Down here, like I said, you can also underline that the order with respect to reactants tell us how much its concentration will affect the rate of reaction. Okay? Now, the order of reaction is a constant for a particular reaction and can only be determined by experiment. Okay? Now, the order is a constant. So, for this reaction, if reactant A has a second order, then it is second order. No matter what temperature or pressure we are having, it is always second order. Okay? And this order cannot be calculated, it can only be experimentally determined. Okay? Now, down here, we have several cases. Case 1 and later on we have case 2, case 3. Now, here, we have something called first order reaction. First order reaction. Let's have a look. Now, what do you mean by first order reaction? Now, first of all, can you look at this reaction? So we have a dinitrogen oxide, okay, and it decomposed to form N2 and O2. All right. Now, if you look at the concentration of the only reactant, and we also look at the initial rate, you notice that, of course, with a higher concentration, it has a faster initial rate, and we try to plot again rate concentration graph. Rate concentration graph. And you notice that in industrial chemistry, we focus a lot in the rate concentration graph, whereas in the core syllabus, we focus on concentration time graph only. Now, if you look at the rate concentration graph, again, you notice they form a straight line passing through origin. And particularly, you notice that if you look at here, if the concentration of N2O is 0.25, the rate is 2. When the concentration doubles, so that it goes up to 0.5 mole per dm cube, then you notice the relative rate or the initial rate also doubles. Okay? Similar idea goes for the concentration increasing from 0.5 to 1. Okay? So you notice that in this particular case, whenever we double the concentration of the reactant, the reaction rate doubles. So in this case, down here, also underline this one, the reaction rate doubles when N2O is doubled. So we will say that the rate equals to K times N2O. Okay? This one rate equation doesn't look very similar. Now, the reason why we can write this one down is because we make use of the fact that doubling the concentration of N2O will result in a doubling of relative rate. So you think about it, if you focus on this equation, if this one doubles, this one also doubles, isn't it? K is a constant that doesn't change at all. So that's why this one, the rate equation, we put it as rate equals to K times N2O. And in fact, there is a power, there is an index hidden. But you know, to the power 1 is basically nothing. I mean, you can simply put down N2O. But what I want to say is, actually, there is a 1 here. And this 1, this number 1 here, is showing you the order of reaction. Order of reaction. And since it is 1, we call it first order. First order. Okay? So we say that the reaction is first order with respect to N2O. Okay? By saying that a reactant is first ordered, that means when we double the concentration of that reactant, the rate also doubles. Okay? So that's the idea. Now, here, some practice question. You are asked to write down the rate equation, and down here you need to deduce the order from the rate equation. And down here we have a short question. So let me do the first one as an example. Now it doesn't matter the equation. You see, when it is second order with respect to NO, and and it is first order with respect to O2. Now, so the equation, we know rate equals to K times AX BY CZ blah blah blah, right? So here, rate equals to K. Now the reactant, the first reactant is NO, so we put down NO here. And then the second one is the O2. Okay? And knowing that it is second order with respect to NO, so the index will be 2. So we'll put a 2 here. And here O2 is first order, so do we put the 1 here? Well, it's not necessary, but you need to know it is first order. So that's it. That's it. Okay? Alright, now you can try this question yourself. Pause the video first, and then after you finish it, resume the video and check the answers. Alright, let's have a look. Now here, first order for propanol and iodine. So I will put down rate. For propanol CH3, CO, CH3. So 1 here, you don't have to put it down. I2, 1, you don't have to put it down. Now 0 order with respect to H+. Now 0 order, H+ to the power 0. Now you know, everything to the power 0 equals to 1, isn't it? So multiply by 1. It's meaningless. So you don't have to include it here. So that would be already the general rate equation. Okay? Down here, deduce the order with respect to each reactant. So here, you know that H2 doesn't have a power, so it is a first order with respect to H2, and it is second order with respect to NO gas. Okay? Now down here, you notice that rate equation is this one. So this one, obviously first order. So first order with respect to CH3,3CBr. Okay? But it's not yet finished. You notice that we need to talk about each reactant. So NaOH is also a reactant. But you see, you can't find it from the general equation. Well, that implies that NO is actually 0 order. So even 0 order, you need to mention. So 0 order with respect to sodium hydroxide. Okay? Now, down here. So we have a graph, and this is when we add excess magnesium to sulfuric acid. So this is a rate concentration graph. You can tell with excess magnesium, basically the concentration of magnesium is negligible. So you focus on the concentration of sulfuric acid, and as you can tell, with a higher concentration, the rate is higher. Okay? Now using this graph to deduce the order of reaction with respect to sulfuric acid, explain your answer. Okay, now you notice that if you try to extrapolate, now you notice that if you are looking at a certain point, okay, you see, for example, for the rate 0.02, the corresponding rate is like 0.22, right? And then you look at 0.4 here, and then going down here, this is like 0.44, isn't it? So you see, when concentration doubles, the rate doubles. So what does it tell you? It tells you that the rate equation would be, and then blah blah blah. I don't know about what magnesium, but you can forget about magnesium. So you notice that they are directly proportional to each other. Okay? So this one is first order. This one is first order with respect to sulfuric acid as doubling sulfuric acid concentration doubles the rate. Okay? Easy. Now, B, under the condition used, the order of reaction with respect to magnesium is 0. So state the rate expression. Very simple. Rate equals to K times sulfuric acid concentration. Okay? That's the idea. Now just one more thing before I move on. You notice that if you go back to here, now you notice the equation here, 2H2 reacts with 2NO. So 2 moles each in the equation. But you notice that the order is not the same as this stoichiometry. In fact, there is no direct relationship between the stoichiometry and the order of reaction. So that's why we say that this order of reaction must be experimentally determined. You can't tell, you can't deduce from the equation. Similarly, like this one, you have no idea, right? You have no idea that sodium hydroxide is 0 order unless you actually carry out experiments to find out. Okay? So this is just to give you an idea that it is impossible to deduce the order from the equation. Okay? Now, next page, we have a second order reaction. Now for second order reaction is when we double the reactant concentration, then it will quadruples the rate of reaction. Okay? So 4-time increase in rate. Now if you look at this one, again, it's a decomposition of a chemical. So if you look at these 4 experiments, you notice that the concentration of ethanol is increasing. So you notice that when the concentration decreased by 2 times, the rate increased by 4 times. Okay, increase 2 times, increase 4 times. So this one tells you that it is a second order with respect to ethanol. Okay? Now, you also notice one thing. If we consider the ethanol concentration as ethanol concentration square, if we put a square here, basically you have this number multiply itself, then you get these numbers in this column, right? You notice that after you have squared the concentration, you notice when the squared concentration multiplied by 4, the rate multiplied by 4. Here, if you look at this one again, like if you compare experiment 2 and 4, when the concentration increased by 4 from 0.04 to 0.16, the rate also multiplied by 4. So you notice one thing, the concentration of ethanol, when it doubles, the rate quadruples. But when we consider the concentration as a squared concentration, then they are directly proportional. Okay, when this one doubles, this one doubles. When this one quadruples, this one quadruples. Okay, so we can say the rate is equal to K times concentration of the ethanol squared. So this one, actually, rate, concentration squared. So this is how we get this equation from this experimental result. Okay, and we say that it's a second order with respect to ethanol. All right. Now, so if you look down here to these 2 graphs, now the rate concentration graph is no longer a straight line passing through origin. Because that makes sense. You see, here, from 0.2 to 0.4, 2 times, right? But now you see, it is changing from here all the way to here. So from here to here, definitely 4-time increase. Okay, you see, 1, 2, 3, I think it's even more than 4 times. But I don't know, the graph may not be that accurate, but you can tell it is actually 4-time increases instead of 2 times. Okay? So, this may not be that useful because it's a curve, it's hard to study. But if you look at this one is a rate against concentration square. Rate against concentration square. And here, we register straight line passing through origin. Okay? So, that's why. Now, if you encounter a bunch of data or you encounter graphs, if you notice that the rate and the concentration, they are in direct proportional relationship, then it is first order, straight line passing through origin. When you encounter the rate against concentration not being a straight line, but instead getting this exponential curve, then it is not first order. It may be second order. It may even be third order. Okay? How can you verify? Well, you can verify this by using this data to plot a rate against concentration square graph. So if this graph yields a straight line passing through origin, then you can tell it is second order with respect to the concentration of ethanol. Okay? So this is how we can make use of the graphs to determine or to deduce the order of reaction with respect to that reagent. Okay? Down here, just to tell you that there are two types of second order reaction. Just now I showed you this one, which is easier to understand because we only got one reactant and it's a second order with respect to that reactant. But here, we have two reactants and each being first ordered. Now remember, we have something called overall order. So if each reactant is first order, the overall order of reaction would be second order. Okay? Now, if the general rate equation is like this, when we double the concentration of A, we will only double the rate. We will not quadruple the rate because they are separate. They are two reactants. Okay? Unless you have this one. If you have this general rate equation, when you double the concentration of A, you'll register a quadruple increase in rate. Okay? So make sure you can tell the difference between these two second order reactions. Okay? Now, case 3, zero order reaction. Actually, in DSC, we only focus on first order, second order, and zero order. Okay, third order, we seldom encounter third order reaction or third order with respect to that reagent. And as a matter of fact, it's quite rare to have reactant being third order. Okay? Now here we say that if we have a zero order reaction, then the reactant concentration has no effect on the rate of reaction. For example, here ammonia decomposed to N2 and H2. You notice that no matter how high the concentration we use, the rate is the same. So you notice the rate concentration graph is like a straight line. No matter what concentration you have, you always register the same rate. So you say that the rate is directly proportional to ammonia to the power 0 because it's zero order. So you notice that the general equation will become rate equals to K. Rate equals to K. In fact, the rate constant would be the y-intercept, okay, of this rate concentration curve. Okay, it's a zero order with respect to ammonia. All right. Now this one will sort of contradict to what we have learned in our core syllabus because we know that when we increase the concentration of reactant, the reaction will increase the rate, isn't it? Because of collision theory. But here, this is showing you that what we have learned in the core topic is actually limited. There are some exceptional cases. This zero order reaction is an exceptional case to the collision theory. Okay? Now down here, some minor remarks, but it's actually quite important. You usually lose marks if you don't pay attention. Units of rate constant. Now, looking at the general rate equation, rate equals to K times concentration. You know that concentration is usually in mole per dm cube. Rate is usually given as mole per dm cube per second because in the core part, we talk about rates equals to concentration of reactant or product divided by time. Okay, so rate is often mole per dm cube per second. Now, for different order of reaction, they have different units. Basically, you do the calculation involving the unit. For example, the second order, let's just say rate equals to Ka squared. Basically, rate is K times A, isn't it? So you know that this one is mole per dm cube per second. This one is mole. If you put them together, mole squared dm to the power negative 6. So you have K equals to rate divided by AA. Okay? Then basically in terms of the unit, you have the mole per dm cube per second divided by mole squared dm to the power negative 6. So you know that when we divide the index, it is equivalent to minus. So mole 1 minus 2 and then dm minus 3 minus 6, okay, per second. But that's why we have mole to the power negative 1, dm to the power negative 3 as negative 1, which is this one. Okay, this is how we can deduce mathematically of the units of K for different reaction. Now here, rate constant K, like I said, K is a constant that won't change, but there is one thing that is changing the K, which is temperature. Because you know that in general, the rate of reaction increases when temperature increases. So the magnitude of rate constant K increases when temperature increases. Very simple. Okay, but there are a few exceptional cases, but you don't have to pay attention to that. Okay. All right, so this page is talking about some graphs related to the rate equation. So we have two important graphs that we need to know, concentration time graphs as well as the rate concentration graphs. Now, we also want to know how these two graphs looks like in the case of first order reaction, second order reaction, and zero order reaction. Now, let's quickly have a look. So for zero order reaction, the rate expression or rate equation would be rate equals to K times A to the power 0, which is basically K. So if you look at the concentration time graph, so it is a straight line decreasing. Now remember, even though the concentration of reactant has no effect on the rate of reaction, still it is a reactant. So as the reaction proceeds, the reactant concentration will decrease. But you notice that it is a straight line instead of a curve, meaning that even though the concentration of reactant has been lowered, the rate of reaction is still the same. So the slope is the rate, okay? Now, the rate concentration graph is very simple. You have a straight line, basically means that no matter what concentration you have, the rate is the same. And this y-intercept is actually the rate constant, okay? Now, the second part here is talking about first order reaction. So first of all, the concentration time graph is a decreasing curve. So you notice that the slope is changing as the concentration changes. That makes sense. And here we have a term called half-life. And half-life basically means the time requires to halve the concentration. Okay? So if, for example, here I make some number. This is like 1. So if it drops to 0.5, then the time it requires is what we call the half-life. Okay? This is the first half-life, and we have a second half-life. So the second half-life is basically the time it takes for 0.5 concentration of A to be consumed so that it becomes 0.25. Okay? And you notice that the half-life is the same. So this is one of the characteristics of concentration time graph of first order reaction, being that the half-life is all the same. Okay? Now, rate concentration graph, we are expecting a straight line passing through origin, and the rate is the rate constant. Okay? This one falls into the straight line curve, y equals to mx. Okay? And the y-intercept is 0, so there is no c there. Okay? Y equals to mx. Okay? Now, for second order reaction, you notice that the concentration time graph is very similar to the concentration time graph of first order reaction. We're still having a decreasing curve. So the difference is that for second order reaction, the half-life is no longer the same. In fact, the second half-life is longer than the first half-life. The third half-life will be longer than the second half-life. So this is the only difference that we can tell when we are comparing the concentration time graph of first order reaction and second order reaction. Now, the rate concentration graph, however, gives us a distinctive difference. So for second order reaction, as the concentration increases, the rate increases, but it increases in an exponential manner. Okay? The reason is because if you look at the rates equation, and if I convert it into this form, rates equals to Ka times A, then you notice that if you use the straight line equation, linear equation, then it will be y equals to mx. So you notice that the slope is Ka. So that means the slope is increasing as A increases. Okay? So that's why here the slope is Ka. Right? Now, of course, this one may not be very useful, especially it is quite difficult to determine the K when the slope is changing. So that's why we will rather plot a rate against A square. If you plot a graph of rate against A square, then you will register a straight line passing through origin. Here, y equals to mx. So from there, we are able to determine the K simply by looking at the slope of the curve. Okay? Now these graphs are very important. Make sure you can deduce the order of reaction based on the shape of the graph, and make sure you tell the difference between concentration time graph and rate concentration graph. You may also be asked to sketch these graphs. Okay? Now at the back here, we have a practice question. So spend some time working on this. Basically, you are doing some matching. And also at the end, don't forget, you need to put down the unit of the rate constant of the three reactions down here. The unit of the rate constant of the three reactions. Okay? Pause the video and attempt these questions. Okay, let's have a look. So, a zero order reaction. So, the rate concentration graph here, A, and the concentration time graph, D. Okay? Now, the unit should be mole per dm cube per second. Okay? Now, for the second order reaction, for the rate concentration graph, we should be expecting an exponential increase. So C is appropriate. And this one, rate against concentration square linear graph must be a second order reaction. Okay? Now, see here, never mind, the rate expression is rate equals to K times isotope concentration, and this tells you that it is a first order reaction. For first order reaction, the rate concentration graph should be a straight line passing through origin, so it is B here, as well as E. Okay, it is a curve, decreasing curve. However, you can tell that the half-life is constant. Okay, so this one E. Okay. The unit I almost forgot. So the unit dm cube mole to the power -1 S1, and this is S1. Okay. All right. Now on next page here, this is actually out of syllabus, but this one is trying to help you to understand what is meant by order of reaction. Like why some reactant could be second order, why some reactant could be first order, and why sometimes the equation, the stoichiometry, is independent to the order of reaction. So now here we say that in fact a lot of reaction occur by more than one step. So when A becomes B, for example here A becomes B, it may not necessarily go in one step. It could be the fact that A becomes C, C becomes E, and at the end becomes B. It could be like this. It could be taking 3 steps. Okay? So when we encounter this situation, we call that this reaction undergoes a mechanism. Okay? It has a mechanism. Okay? A mechanism is a stepwise description of a chemical reaction. So in this reaction mechanism, we have 3 steps. Now, whenever we have a reaction mechanism, each step, some must be faster, some must be slower. So we are particularly interested at the slowest step. The slowest step is what we call the rate determining step, because that step will determine how fast the overall reaction proceeds. Okay? Now think about it. Let's just make some numbers. Let's just say the first step take 100 seconds, and the second and the third step each take 1 second. So you can tell, whenever some A becomes C, then very quickly C will become E, and very quickly E will become B. Okay? So if we are able to speed up the first equation, so you notice that the overall reaction takes maybe 102 seconds, right? So if we are able to increase the first step, increase the rate of the first step by double, that means it takes half the time to complete, then it will take only 52 seconds. So it's like speeding up the overall reaction from 102 seconds to 52 seconds, almost like double the overall rate. However, if we are able to double the speed of step 2, so now it takes 0.5 seconds, then the overall reaction rate takes like 101.5 seconds. Actually, it has almost no effect to the overall rate of reaction. So you notice that the overall reaction rate depends on the slowest step. So if we are able to speed up the slowest step, then the overall rate will increase. So everything boils down to the slowest step, and that's why the slowest step is called the rate determining step. Now in this particular mechanism, the rate determining step actually involving A only. It does not involving C, D, E, okay, nothing. So this reaction is first order with respect to A and zero order with respect to other things, okay? Because it all boils down to the concentration of A here, okay? Now down here, this is another example, so 2x plus y becoming z. Now this time, the mechanism has 2 steps. The second step is the slower step. Now you notice that the second step involving x reacting with m to form z, and this is a slower step. So the rate is determined by the speed of second step, which include x as the reactant. So you notice that the rate will be equal to k times x. Okay? Now think about it. The first step is very fast, right? So whenever you have x and y, they will quickly become m. Okay? So the supply of m is abundant. There's always m hang around. It all depends on the concentration of x. So if we have a high concentration of x, then it is able to react faster with m to form z. So everything boils down to x, not m. Okay? So that is what we call the reaction mechanism. And now you know why for different reaction, they can have different order with respect to the reactants. Even though according to the equation, 2x react to form z. But it turns out that the order with respect to x is 1. Okay? Now these mechanisms is worked out through experiment. And these are all proposed mechanisms. So that's why we say that we cannot determine the order from calculation. We cannot determine the order from the equation because we have no idea how the mechanism takes place. Okay? So that perhaps gives you more ideas about how order works, how give you more idea about the meaning of order of reaction. Okay, so that's it for this video.